Welcome, novice pilots. Grab your headsets and settle right here into the cockpit for today's pre-flight briefing. In this explanator, we're going to completely demystify wing design, specifically the aerodynamics of airfoils. So if you're just starting out in aviation and want to know exactly how these massive metal machines actually stay airborne, well, you are absolutely in the right place. But before we're cleared for takeoff, I want to invite you to officially enroll in our flight school. Just hit that like button and subscribe below to log your training hours. It really helps us keep these briefings coming. All right, strapped in? Let's go. Let's quickly run through today's flight plan. First, the anatomy of an airfoil. Second, how wings generate lift. Third, we'll look at Bernoulli and Newton. Fourth, adapting wings for speed. And fifth, winglets and tip vortices.
Starting off with Section 1, Anatomy of an Airfoil. Let's establish that basic vocabulary so you know the parts before we actually fly the plane.
We'll begin by identifying the two extreme ends of the wing's profile. You see that rounded end on the left? The part that faces forward into the wind during flight? That's called the leading edge. And all the way at the back, we have the exact opposite end, the trailing edge, which is quite narrow, kind of tapered down. So the air meets the leading edge first, and it leaves at the trailing edge. Simple enough, right?
Now notice the technical difference between our two main reference lines here. The straight wing chord line connects the leading edge directly to the trailing edge like a ruler. But the curved, mean camber line, that one is perfectly equidistant from the upper and lower surfaces all the way across. And the distance between that straight chord line and the curved mean line tells us the magnitude of the camber, basically the curvature, at any given point on the wing.
And this brilliantly illustrates that difference in camber. You'll notice the upper camber has a much more pronounced sort of scooped curvature to it, while the lower camber is usually a somewhat flat surface. This specific difference in curvature between the top and the bottom, it isn't just for looks. It is the fundamental design element that ultimately determines the wing's overall aerodynamic efficiency.
Moving right along to Section 2, How Wings Generate Lift. Let's see how these specific shapes actually interact with the air to get us airborne.
Okay, have you ever stuck your hand out of a fast-moving car window on the highway? Think about what happens. If you keep your hand perfectly flat and level with the wind, it just cuts right through. But the second you incline your hand slightly against the wind, it deflects the oncoming air downward, which literally pushes your arm upward. Or you tilt it down and your arm gets shoved down. This everyday experience perfectly demonstrates how the angle of attack creates what we call flow turning, deflecting the air to create a measurable directional force.
And honestly, this explains exactly why flat surfaces, like those paper airplanes you folded as a kid, which are basically just flat plates, can still fly. It's the exact same deal for the symmetrical airfoils used on high-speed aircraft or helicopter rotor blades, where the upper and lower surfaces curve identically. Even without that pronounced upper camber we talked about a minute ago, these shapes can still produce lift just by changing their angle against the oncoming airflow.
Okay, Section 3, Bernoulli and Newton. The physical laws that make all this lifting action happen really boil down to these two famous names.
First, the oncoming airflow hits that leading edge and virtually stops at what we call the stagnation point, right before it splits. Second, because of that pronounced upper camber, the air traveling over the top is forced to move much faster to keep up. And finally, that faster air meets the slower air back at the trailing edge, creating a downward-backward flow called downwash. It's an elegant process that perfectly combines the laws of pressure and air forces in a totally logical aerodynamic flow.
Here we can clearly see the difference between our two main physical principles. Applying Bernoulli's principle of pressure, that increased airspeed we just saw across the top of the wing produces a significant drop in pressure. Meanwhile, we apply Newton's third law. Every action has an equal and opposite reaction to the trailing edge. That downward-backward downwash from the top surface forces a reaction that results in an upward-forward force on the airfoil itself.
To make it super simple, just use this comparison. The low pressure above the wing, which is caused by that fast-moving air, acts almost like a vacuum, naturally pulling the wing up from above. Underneath, because the airflow was slowed down, a positive, high-pressure force is created that physically pushes the wing up from below. So you really need both actions, the pull from the low pressure above and the push from the high pressure below to achieve total lift.
Let's pivot to Section 4, Adapting Wings for Speed. We're going to explore how aircraft vary in their wing design depending entirely on the specific type of flight they're built for.
This perfectly illustrates a major engineering dilemma. The absolute most efficient airfoil for producing the greatest amount of lift is one with a deeply concave or scooped-out lower surface. But as a fixed design, a deeply concave wing creates massive wind resistance, or drag, sacrificing way too much speed. On the flip side, a perfectly streamlined teardrop shape offers incredibly low drag for high-speed flight, but it sometimes doesn't have enough lifting power to actually get a heavy airplane off the ground. So modern planes have to strike a really delicate aerodynamic balance between these two extremes.
So, how exactly do heavy, high-speed jets manage to land safely at slow speeds? Well, advancements in engineering solved this. High-speed jets use leading-edge Kruger flaps and trailing-edge Fowler flaps. When these flaps are extended out from the basic streamlined wing structure, they literally modify the basic wing into that highly efficient, classic concave form. This generates the massive amount of lift required for slow flight conditions, like takeoff and landing. It's honestly a real game changer.
All right, pay close attention here because this is an actual safety briefing. The average of all these pressure variations we've been discussing is called the center of pressure, or CP. And as your instructor, I must emphasize this absolutely critical safety point for your flight maneuvers. As you change your wing's angle against the wind, that center of pressure physically moves. It actively shifts forward at high angles of attack, and it moves aft or backward at low angles of attack. This directly impacts the aircraft's aerodynamic balance, the structural loads on the wing, and most importantly, your ability to maintain control in the cockpit.
Finally, Section 5, Winglets and Tip Vortices. Now we have to look out at the very tips of our wings, stepping into the third dimension of aerodynamics.
Nature always seeks balance, right? Which means high pressure always seeks out low pressure. Because of this, the high-pressure air from the bottom of the wing aggressively curls around the wingtips, desperately trying to reach the low-pressure vacuum on top. This action creates violent, rotating downwash currents trailing behind the plane, which are called wingtip vortices. These vortices are a huge problem because they drag down our overall flight efficiency and actively reduce lift.
To solve this massive drag problem, aerospace manufacturers use a couple of really clever methods to counteract the flow. They can taper the wingtips, which naturally reduces the pressure differential and simply smooths out the airflow. Or, and you've definitely seen these on commercial flights, they install vertical winglets. These winglets act as literal physical dams. They block the high-pressure air from curling over, preventing the vortex from ever forming in the first place.
So, the next time you're observing aircraft at the local airport or just looking up at the sky, use these quick tips to easily identify wing types. Look for those vertical winglets on modern commercial jets. Try to spot symmetrical airfoils on helicopter blades spinning overhead. Notice the deeply pronounced upper cambers on smaller, light training aircraft. And definitely watch for those Fowler and Kruger flaps extending out of the wing when a jet is coming in for a landing. It is so amazing to spot how these different shapes impact flight efficiency in the real world. As you pack up your flight bags and watch those planes soar overhead after today's briefing, ask yourself, which perfect combination of pressure, shape, and angle is keeping that specific plane safely suspended in the sky? The physics of flight are happening right above our heads every single minute of the day. Thanks for joining me in the cockpit today, novice pilots. Keep your eyes on the skies, and I'll see you in the next explainer.